Welcome to Arithmetic Sequences. These you have come across in the past. You will have encountered them earlier in your mathematical career, probably known as linear sequences. They're the kind that go up in regular steps. Now, technically, they could go down in regular steps. The idea is they have a common difference between one term and the next. In other words, what you add every time is the same. Maybe you're adding 5, maybe you're adding -2, but every single sequence is a linear sequence, or what we're now going to call an arithmetic sequence, if the terms are changing according to a regular additive pattern. If you plotted the points on a graph, you would see them go up in a straight line, hence the name. Now, before we begin with that, we're going to delve into a little bit of the background for this topic, because arithmetic sequences is really setting the scene and laying the groundwork for something called arithmetic series, which is essentially a sequence of numbers, a pattern of numbers, but added together, where we start asking questions about what the numbers add up to make. So for instance, here's a pattern of numbers. This is one of the simplest linear sequences you would come across, because you're just adding 1 every time. We start at 1, we add 1 every time. But we're only going to go up to the 40th number, and then I'd like you to pause the video and have a go at adding all of these 40 numbers together. But there's a couple of provisos. I don't want you to use any artificial calculating devices. If you use any clever methods, then you need to be able to justify them. So try to avoid reaching for a calculator, your phone, a pen and paper, whatever else. But remember, we're doing maths now, so if you find yourself spending 10 minutes just adding numbers together, you're not learning anything. Have a pause and a think about what shortcuts might come in handy. And when you've given it a minute or two, wherever you've got to, unpause the video and I'll talk through some approaches you might have taken. Okay. Generally speaking, when people calculate something like this, there's a few things that they might try. And if you've tried some of these, you can feel pretty smug about yourself. If you've come up with something different, you can also feel pretty smug, as long as your method works. But if you didn't think of these, don't worry. It's the kind of thing that you wouldn't necessarily just jump to on your own unless you spent some time sitting and thinking about this kind of thing. But one nice approach here is to look for the average of the numbers. We've got numbers that are going up in nice regular steps. So what that means is the mean average and the median average will be the same. The mean average is directly connected to the total of the numbers. There are 40 numbers. So if we knew the mean average, we could multiply that number by 40 and it would give us the total, because the mean is the total divided by 40. The median, on the other hand, gives you the number exactly halfway along. And we don't need to add up all the numbers to find out what's halfway along. The numbers 1 to 20 form the lower half of the list, and the numbers 21 to 40 form the upper half. So the middle of the list must be exactly halfway between 20 and 21. So the median is 20.5, but because of the symmetry of this sum, the mean is also 20.5. If you multiply 20.5 by 40, that will give you the overall total. Another approach that works quite well, that's perhaps a little stranger, is to look for pairs of numbers that add together to make the same thing. So 1 and 40 add up to make 41. 2 and 39 add up to make 41. 3 and 38 add to make 41. There's a pattern in there. The lower numbers are increasing one at a time. The higher numbers are decreasing one at a time. So the overall total stays the same. That's quite a clever trick as well, and that takes advantage of the fact that if the numbers we're adding are all the same, we can just use multiplication. As long as you can figure out how many pairs of numbers you're dealing with and you know what each pair adds up to, you can use that. In fact, that brings us to an interesting story. Karl Gauss is a very famous mathematician who has contributed immensely to all sorts of areas of maths, but in particular his work with numbers. And it began at a very early age. This was the kind of kid who thought about numbers deeply and a lot. So one day, so goes the story, his primary school teacher set his class the task of adding up the first 100 integers. I suppose the idea would be they get to practice adding numbers and he gets to have a little bit of a sleep. But Karl Gauss came back with an answer within moments, maybe a minute or so. He comes up to the desk and he's got an answer. He gets 5,050, which the teacher has to then check by hand because he hasn't worked it out himself. He figured he'd have plenty of time to catch up, or maybe wait until 3 of the cleverest kids have worked out the number and then verify by looking at the 3. But it turns out he is correct. 5,050 is correct, but there's hardly any working out on Gauss's slate, so it's not clear how he's done this particular thing. And obviously, there's a shortcut involved, and that's what maths is all about. The purpose of thinking is to stop thinking. The aim of mathematics is to find a lazy, or to put it in a nicer way, a more efficient way of looking at a problem so that we don't have to keep working at something. We can get to the end or find a solution to the problem more efficiently. And that's what Gauss had done. Let's go through in detail the method that he employed. So the first thing is to imagine you've got 2 copies of your list. We've got the numbers from 1 to 100. What if we also had the numbers from 100 to 1? You'll notice this resembles a little bit the method we talked about where you add the first and last numbers in the list. But the advantage of this version is that you don't have to worry too much about when you meet in the middle. The next thing to do is to add up each pair of numbers. So it feels like we've got a problem which is now twice as hard because we seem to be trying to add up 2 lists of numbers, but turns out that'll be easier than 1. And we're going to do them pair by pair. 1 add 100, 2 add 99, 3 add 98, and so on. And you don't need to do this for every single pair because once you've done a few, you'll quickly see the pattern. In each case, and you can convince yourself of this and rigorously prove it to one another, you can see that the left-hand column, the numbers are increasing by 1 for every sum, and in the right-hand column, they're decreasing by 1. So the total is never going to change, and every single pair adds up to 101. Now, here's the clever bit. There are 100 numbers in that list, and they're all the same number. We don't have to add, we just need to multiply. So 101 is the size of each term, and there are 100 terms, so we have a total of 10100, or 10,100. All you have to do at the end is remember that what you've done so far is found the total of 2 identical lists. If you want the total for just one list, you halve your answer. Elegant, isn't it? I'd like you to have a go at the same sort of trick now. Try it with the numbers 1 to 20. You might even want to try it with the numbers 1 to 40 like you had at the beginning and see how efficient this trick works out to be. Pause the video, give it a go, and then check back. Okay, hopefully you managed to make it work. You can think of a list reversed, you can add them, you can think about how many of those numbers you've got. We now have 20 numbers and each of them is 21. You can multiply those together, you can halve your answer, and the sum of the numbers from 1 to 20 is 210. Here's a couple of challenges. I would encourage you to pause in a moment and have a go at these 2. Think carefully about how the sum from 1 to 200 is different to the sum from 1 to 20. And then think about the sum from 5 to 100 but going up in 5s, and see if you can see how that relates to the total for 1 and 2 all the way up to 20. Pause, have a go at those, and then write down what your findings are. We're not going to discuss those, but it gives you a chance to think a bit more deeply about this process and how it scales as lists change. Okay. The next thing I want to look at is the more general version. We're going to make this more abstract and imagine a list of numbers that start at 1, they go up in 1s, and then they finish at any number you like. So we'll call it n for now. But if we can generate a formula, then no matter how far I want to add the numbers, I don't need to think about the trick. I can delegate the process to a formula. So we'll follow exactly the same process. We'll write an identical list backwards, which starts at n and goes down in ones all the way to the beginning, 1. When we add the two columns, term by term, we have 1 plus n, 2 plus n minus 1, 3 plus n minus 2, and so on. Every single term is n plus 1, one more than the number that we decided to add up to. Just like when we did 1 to 100, every number pair added up to 101. Now, how many numbers do we have? How many numbers in that green list? Well, the original list we were trying to add up had n numbers because they were the integers from 1 to n. So we just multiply n by the number that we have in our list over and over again, which is n plus 1. And the final step, to find out the total sum for just one of the original lists, you divide by 2. So here we go. We have a half n times n plus 1. In general, we can write it like this. 1 plus 2 all the way up to n is equal to a half times n plus 1. You can test it out for yourself with a few numbers. If you want the sum of the numbers from 1 to 3, you do half times 3 times 4. If you want the sum of the numbers from 1 to 10, half times 10 times 11, and it will always work. But there should be a bit in that that seems a little strange to you. It certainly did for me when I first saw this. I had a niggling feeling about this half. Because on the left-hand side, there are no fractions. The left-hand side looks perfectly sensible. We're adding up a whole bunch of whole numbers. So where does that half come from? And surely that's potentially going to throw a spanner in the works. Because anytime we end up with a number that gets divided by 2, unless we were dividing an even number by 2, then we're potentially going to end up with a non-integer. But we can't possibly have a number that's not an integer when we're adding up the numbers from 1 to n. So have a think about why this formula always works, and think carefully about n times n plus 1. If it helps, a really good idea here is just to try substituting some numbers in and see why we never get a problem. And when you've started to spot what's happening with numbers, see if you can generalize your argument. The clue here, the secret, is to think about the different cases. What happens if n is an odd number? What happens if n is an even number? And what will happen to the overall product, n times n plus 1, and therefore what happens when you multiply that product by a half? There's another way of writing this, which is the more common way of representing this result, and it might look a little mysterious and daunting to you if you've never seen summation notation before. This big fancy symbol here is a Greek letter sigma, which is basically the S, and it stands for sum. So when you see that symbol, it means I want to add up terms of the following form. And in this case, we're adding up terms that look like R. It's a very straightforward one. But the thing is, R represents not just a single value, but a sequence of numbers, a range of numbers. And that range starts with R equals 1, and it goes all the way up to R equals n. It includes both endpoints. So when we say the sum from R equals 1 to n of R, what we mean is start by setting R equal to 1 and put that number down. And then set R equal to the next number up and put that number down next to the first number and add them together. And then increase R by 1 again and then put that number down. And we continue to do that, generating the numbers 1, 2, 3, 4, and so on, until we reach the upper limit, n, and then we stop. And we calculate the total sum of all of those numbers. This might remind you a little bit of integration. And that's because in integration, we use the Latin letter S for sum. The sigma that you see, the capital sigma on the left, is a discrete sum, which means we're adding distinct separate numbers, and we have a certain number of them to add up. Whereas on the right-hand side, it's a continuous sum, because technically integration is about adding up the total area across a given interval. So it's not about separate pieces being added together quite so much as it is about tiny infinitesimal strips of area being combined, and we want the entire area under a curve, a smooth curve, which changes continuously. So it's a really crazy idea what integration does, but there are connections between integration and summation like this. We're now going to talk just a little bit more about that summation notation so that you can get a sense of how it works when we change up what goes on inside. If you only ever see one example of it like this, it's going to be hard to see exactly how it could be modified. This example basically tells us what Gauss found out, that the sum of all the integer values from 1 to 100 is 5050. The lower limit for r is given as 1. The upper limit at the top of the summation symbol is given as 100. So we go through values of r from 1 to 100 and we add them all up. Now what if instead we went through values of r from 3 to 6, and instead of just adding up the values of r, we added up the values of r squared? And then perhaps we can try this slightly different one, from r equals 3 to 6 of 2r. So when r is 3, we work out 2 times 3, and when r is 4, we work out 2 times 4. When r is 5, we work out 2 times 5, and when r is 6, we work out 2 times 6. Then we add together all of those terms. I'd encourage you to pause at this point and see if you can write down the 4 terms that each of these summation expressions represents, and then calculate the value. Writing down the expression is just as important as calculating the final value in this case. When you're ready, we'll move on. So for this one, we have the sum of the square numbers from 3 squared to 6 squared. For the next one, we have the sum of the even numbers from 2 3s to 2 6s. And for the last one, you've got to be a little careful with this, because you can think of it as a combination of the previous two, but it's not the same as just adding the 2 previous totals and then adding 1, because that plus 1 is part of the entire summation term. So we're doing 3 squared, add 2 3s, add 1. And then 4 squared, add 2 4s, add 1. 5 squared, add 2 5s, add 1. And 6 squared, add 2 6s, add 1. If you were keeping track, there were 4 1s in there because there were 4 different values for r. So even though it's just a constant term, that 1 at the end, it has an effect which depends on the number of different values for r. In this case, you can actually go through and calculate. If you do 3 squared, add 2 3s, add 1, and so on, these are the numbers you get. You might recognize those: 16, 25, 36, 49. They are actually square numbers in their own right. And if you think carefully, you'll see why they're coming out as perfect squares. The algebraic expression, r squared, add 2r, add 1, is itself a perfect square. You can complete the square and you'll find out it gives you exactly r plus 1 in a bracket squared. So you can think about how that perhaps corresponds to the original summation at the top of sum of r squared, and how perhaps a change in the limits for r would allow you to get the same result from that one. The next section here is arithmetic sequences. We're going to look at the notation and the key terminology associated with the arithmetic sequence. So we've had a bit of an introduction. We've seen some things you can perhaps ask about them. In particular, we've looked at how you might be able to add the terms of a simple arithmetic sequence together. Now we're going to get a bit technical and think generally about what makes a sequence arithmetic. And this is the key feature. The terms in an arithmetic sequence have a common difference d. In other words, if you look at how much you add to get from, say, the 3rd term to the 4th term, it's the same as what you add to get from the 4th term to the 5th term. Each pair of consecutive terms has a difference which is the same. And it's not just that they have the same difference, but it's the same direction as well, if you like. So you're adding, in this case, 10 every time. 25, add 10 gives 35, add 10 gives 45. So this sequence is defined by starting at 25 and going up in tens. And that's what makes it an arithmetic sequence. Based on that definition, can you work out which of these sequences is an arithmetic sequence? If it is true to say that there is a number that you could add each time to get from one term to the next, a fixed number, then it will be an arithmetic sequence. Pause and have a think and see if you can make a decision for each of these four possibilities. Okay, starting with the first one, we have a yes. 1, 2, 3, 4, 5 is probably the most basic of arithmetic sequences you could come up with, and it's clear that there is a common difference of 1. We add 1 to get from each term to the next. For B, it starts at -9, goes up to -4, and then to 1, to 6, to 11. This one works just as well. We're adding 5 every time. For C, this might have given you pause because it doesn't seem like it's going up or down. But 0 is a perfectly valid number, and although it does feel different to other numbers, it's going to work just fine, and none of the rules and the formulae that we're going to create here break down when we have an arithmetic sequence with a common difference of 0. It just gives you a simpler version, a trivial version of the sequence, if you like. So this one is still linear, but it's a constant linear sequence. A little bit like a horizontal line on a graph, we'd still treat as a line, but it's simpler than a line that has a non-zero gradient. And the last one, this one you might have been skeptical of because we don't know what x is, but in fact, any rule that works with numbers like a and b and c will also work just fine with algebra. It turns out it doesn't matter what x is because we're still subtracting x squared over 2 every time. And that number is the same for each pair of terms. So yes, we can treat that thing as an arithmetic sequence. If you've had a read of the bonus follow-up on the bottom, a geometric series has a similar pattern to it, but instead of adding the same thing each time, you're multiplying by the same thing each time. So you might want to pause and have a think about, can you come up with any sequences that are both geometric and arithmetic? And if you can you come up with a complete list of all the possibilities for that kind of situation? And if you can't, can you prove that it's impossible? Now we're going to look at an arithmetic series. So just like we did when we looked at 1 plus 2 plus 3 all the way up to 100, we're now considering the same pattern of numbers, but adding all the numbers together instead of simply focusing on what the numbers are in each position. So we remember what Gauss did with the numbers from 1 to 100. He wrote them forwards and backwards, looked at the sum of each pair, put them all together. If we can find that total, then we can find the total for the original sequence of numbers added together. We're going to be able to make use of his trick with not just an arithmetic series that has the numbers 1, 2, 3, and so on, but with any arithmetic series. But in order to do that, we're going to need some notation. We're going to need to be able to describe all the things we want to talk about. So we've got a few letters down the side there, A, D, N, UN, and SN. We're going to start with the first one. A represents the first term of the sequence or series. That means whatever number comes at the very beginning, that number is A. So with the sequence that we've got right at the top of the page, 25 add 35 add 45 add 55, A would be 25. It is the value of the first term. D, we've mentioned already, D is the common difference. That is the number you would add every time. So for the sequence, or the series rather, that we've got at the top there, D would be 10 because we add 10 to get from one term to the next. N itself, you might struggle to describe fully, but you already have some good idea, I think, of what it means because you've used the term N when you refer to the nth term of a sequence. We can think of it in two ways, either the number of terms that we're interested in at any given moment, or the position of the term that you're interested in. So for instance, if I was talking about the 45 in the series at the top, then I would say n is 3, and the nth term, if n is 3, would be 45. The third term is 45. So in that context, the term itself is 45, but n would be equal to 3. It's the position of the term. And that brings us to UN, which is the general notation used to refer to the nth term of a sequence. So we could say U3 equals 45, for instance. And finally, SN. This is the one where it really matters that we're talking about a series rather than a sequence. The words may feel interchangeable, but generally speaking, sequence is used to refer to a pattern of numbers where we know the numbers and the order they come in, but a series refers to the sum of a pattern of numbers. And in this case, Sn corresponds to the sum of the first n terms. So starting from the beginning, the first term, which might also be called A or even U1, we add up all of the terms up to and including the nth term, Un. So if I want S5 for Karl Gauss's sequence, then I will be interested in the sum of the first 5 terms, 1, 2, 3, 4, and 5, for instance. To check you understand, I'd like you to pause briefly and jot down for me the values of A, D, U5, and S4 for the series here, 3 root 2 and 4 root 2, etc. What you should have for this, your first term is just the number at the front, so that's 3 root 2. The common difference, D, will be what you add every time. Be careful with this, it looks like you're adding 1, but what you're adding 1 of is 1 root 2. So the common difference here is root 2. U5 means the 5th term. It's not shown on here, I've only given you the first 4, but it should be clear from the pattern that the 5th term will be 7 root 2. And lastly, S4 means the sum of the first 4 terms, and they're already shown on the screen, so all you would need to do is add them together, and you should get 18 root 2. Next, we want to talk about another generalization. The algebra just keeps getting more and more in here, and now what we're looking at is effectively a description of every arithmetic series ever. Just like we've learnt to use expressions like 2n plus 1 to represent any and every odd integer ever, we can use this algebraic description to describe any arithmetic series, because they all start with a first term which is a, and to get to the next term you add d. So if the first term is a, the second term will necessarily be a plus d. And term number 3, because you've added d one more time, you've added d twice because you started at the first term and you haven't had any common differences at that point because the first term is just a, but you've added d twice to get to the third term, so now you have a plus 2d. So it's worth getting clear in your head this. This is the nth term of the series. The first term is a plus 0 lots of d. The second term is a plus 1d. The third term a plus 2d. The 10th term a plus 9d. And therefore the nth term a plus n minus 1d. For instance, if I set a value for a and a value for d, we could generate this particular series. We can see that each of those terms corresponds to the expression above. 13 is 3 plus 1 lots of 10. 23 is 3 plus 2 lots of 10. So the third term is the first term plus 2 lots of the common difference. And at each point, the number of d's that you've added is just 1 less than your current position. This is a really important formula and it is not provided in the Edexcel formula book for A-level maths. So make sure this you learn. It should be something that sticks in your head because of why it works the way it does. So I'd highly encourage you to think of this not just as a standalone formula, but think of it in the context of the series that I've written out at the top of the slide here. A plus D plus A plus 2D and so on. Because then it'll stick in your head why we always have a and then a bunch of d's added on, and hopefully the weirdness with the n-1 will also make sense to you. Let's try one example with an arithmetic series which is going backwards, if you like. Think carefully and pause so that you can write down the values of a and d and u5, the 5th term, and s5, the sum of the first 5 terms. What you should have is a equals 10. That's the very first term. It just means the number at the beginning. D equals -2 because the common difference is what we add every time. That's how it's defined, which means if you're taking away 2, then the common difference is -2. 10 add -2 gives 8. 8 add -2 gives 6, and so on. U5 just means the term in position number 5. In this case, that's 2. And S5 is the sum of the first 5 terms, which are the 5 terms you can see on the screen. There's a few questions here I'd like to try, so I'd encourage you to pause the video in a moment and have a go at each of these. We're talking about the value of a particular term or finding the position, in other words, what is n for a certain condition. And you're going to need to make use of the UN formula. Remember, it's not one you'll be given in the formula book, but for now, of course, be referring back to it and make sure you're familiar with it. All right, for the first question, the value of the 20th term, we're going to need to use the UN formula. And if it's the 20th term, then n is 20. We put in U20, which is a plus n minus 1. D, in other words, a plus 19d in this case. But we also know the values of a and d. We'll find that in general, even if an exam question doesn't ask you for a and d, they are almost certainly going to be important things to work out because all the other rules and formulae and shortcuts tend to be written in terms of those two values. In this case, once you substitute in everything you know, a, d, and n, you're just calculating a value, -28. And I'd encourage you to check that this is sensible. Our series is going down in 2s, and it starts at 10. By the time you get to the 20th term, it's going to be lower than 0. That should be fairly obvious. And it's also going to be an even number. So far, so good. It certainly looks ballpark the right kind of result. Find the position of the term which is equal to -400. So this is flipping things around a little bit and saying we know the value of the term. What we don't know is the position of the term. So what we're substituting in here is actually the value of un, which is -400, but we don't know the value of n itself. So I've got a plus n minus 1d. I've written it as 10 plus n minus 1 times -2. And then instead of writing un, we've written -400 because we know the value of un. Once you've got that, it's just a case of rearranging and simplifying, and you'll find an answer of n equals 206. And that also seems to make sense, approximately 200 terms, because we start at 10 and we lose 2 every time. So if you wait for a couple of 100 terms to go by, you'll have dropped by roughly 200 times 2, about 400. We've got to 206 because we needed enough terms to go all the way down to -400, and we started slightly above 0. Find the position of the first term which is less than -100. Got to be a little careful with this one. Because it's an inequality, it's normally a good idea to set it up as an inequality. Un is the term that we're interested in, and we know that it has to be below -100. So again, we don't know what n is, but we know an inequality statement about un. So we can enter that information in. 10 plus n minus 1 times -2 again, but this time is less than -100. Now, we can solve this inequality, but we have to be a little bit careful because there are negatives all over the place. And although you're allowed to add or subtract anything you like, if you multiply or divide by a negative number whenever you're dealing with an inequality, the inequality sign switches around. This is important because if you miss it out here, you'll end up saying something about n which is effectively the opposite of true. So when we simplify this, whether we choose to rewrite the inequality by adding or subtracting values to each side, or if we divide through by a negative number, we should find in the end that n has to be greater than 56. Because it asked for the position of the first term which is below -100, not at least as low as, but actually less than, we have to go beyond 56 to find an example of a term that's low enough. If you check back, you'll find that U56, the 56th term, is actually equal to exactly -100. So we need to go to the next one along, which will be presumably -102. The last question I like because it makes you think more carefully about the sequence in general. The maximum possible value of Sn. Well, if we don't put a limit on n, then in theory you could just keep going for as long as you like. You could just continue to add numbers all the way down to the nth term, and if n can be as big as you want, you could make this series as big as you like, so the total sum that you're trying to add up would be as long as you want. However, that doesn't necessarily mean it can be as big as you like, because as you can see, if you investigate just a few terms further along, you'll notice that we're just adding negatives. So beyond a certain point, we're not adding anything to our sum. If you have S1, that's 10. It's the sum of the first 1 terms. S2 is 18. S3 is 24. S4 is going to be 28. S5 is 30. S6 is also 30. We're just adding 0. S7 is 28 again. And S8 will go down to 24, and so on. So the sum reaches a peak and then starts to tail off. The simplest way to say it is just that because the terms are negative whenever n is bigger than 6, we might as well quit while we're ahead and stop at S5 or at S6. Doesn't matter which. It was asking for the maximum possible value for Sn, and the maximum possible value is 30. You get that when you add up the first 5 terms, like we did at the beginning here, or when you add up the first 6 terms, because the 6th term doesn't add anything. This type of question is a classic. The examiner will give you clues relating to an arithmetic series or sequence, and it'll be your job to reverse engineer the key information about that sequence or series and then use it to solve a problem. Hopefully, they've made part A here, finding the first term and the common difference. Even if they hadn't, that should be the first thing that springs to mind. If you've got a couple of clues about your sequence or series, like we have here, then you need to be making use of those clues to first find the first term and common difference. And then, using those values for A and for D, you can calculate anything else that you need because we've got formulae for those. So let's start with that. How do we get the first term and the common difference? Well, the best way is to make use of our notation. The 5th term is 52. We can write that literally as U5 equals 52. And we can do the same thing with the 9th term, U9 equals 100. And of course, we know we'll be making use of our nth term formula, UN, so I'm going to write it down right at the very beginning. That will also help me when it comes to the next step, because I know n, so I can rewrite both of those as equations involving a and d. A plus 1 less than 5 times d, and a plus 1 less than 9 times d. At this point, all that we need to do is solve simultaneously. Each clue on its own is not enough to tie down the sequence we're dealing with, but this is a bit like me telling you 2 points on a straight line. Any one point is not enough for you to know where the straight line is, which way it's pointing. You only have a single piece of information about where it goes. But as soon as you've got a second point, there's only one straight line that can pass through those 2 points. When we solve simultaneously, which you can do either with a calculator or pretty quickly in this case with a bit of elimination, we find a value for D and a value for A. This sequence apparently starts at 4 and goes up in 12s. And it's not a bad idea to just verify that. If the numbers involved are small enough, you can start at 4. You just need to add 12 4 times to get to the 5th term. And yes, that does get you to 52. And if you go up another few times, you'll get to the 9th term. And yes, that will give you 100. For the next bit, hence calculate the value of the 14th term. Well, now we've got A and D, calculating the 14th term is straightforward. We still need the UN formula, but we now know A and D, so the only unknown in there is N, and they've asked for the 14th term, so N is 14. When we substitute that in, we should get 160. And again, you could check, 14th term is not far from the 9th term. If you add enough 12s, does it get you to 160? And the third question is a bit more nuanced, the position of the first term which is greater than 1,000. So we start by writing out the formula we already have. We know A and D, so we can give a more specific formula than the general rule for UN, 4 plus 12 times n minus 1. But then we're told that UN has to be bigger than 1,000. So we substitute in the expression for UN, and we put greater than 1000. Now all we're doing is solving a linear inequality. There shouldn't be any issues with dividing or multiplying by negatives in this one, so we can simply rearrange and simplify things, and we should end up with n minus 1 is more than 83, so n itself is more than 84, and n, therefore, since it's the first term which is greater than 1000, is going to have to be 85. It's the very lowest integer that satisfies the condition is bigger than 84. You can even verify this for yourself. If you try putting 84 into the formula for the nth term, it comes out as exactly 1000, which is not greater than 1000. Whereas if you put the next one in, it comes out as a number slightly higher. Now you should be able to try a few of the questions from the Pure Year 2 book. Exercise 3A, questions 4, 7, and 8 will be good starting points. But feel free to try a few others from earlier in the exercise, or even some of the later ones if you're feeling comfortable. In this section, I'm going to show you where the SN formula comes from. Don't worry too much if this feels a little confusing, because the SN formula, unlike the UN formula, is provided in the formula book, and you won't be expected to derive the SN formula. However, I like the fact that it's linked so nicely to Gauss's trick for adding up the numbers from 1 to 100, so I'm going to demonstrate algebraically where it comes from here. So here is Sn written out in the most general form. There's the first term a, the second term a plus d, all the way up to the nth term a plus n minus 1 d. And then we write it out again, but we write it backwards. So you can see the first term now appears on the far right, and the last term from before appears on the far left. And now we're going to pair them up. So the first term of each and the last term of each, for instance, we're going to put those together, we're going to put these together, and we're going to see what happens if we do that for every single term. A plus d, add a plus n minus 2d, and a plus 2d, add a plus n minus 3d, and so on. And you should start to see, it doesn't matter which pair we pick, the same kind of pattern happens that we saw when Gauss performed his little trick. A plus n minus 1d is just 2a plus n minus 1d. As you move to the right in the top equation, you're gradually adding d's, and as you move to the right in the bottom equation, you're gradually subtracting d's. So the overall sum never changes, and we just have a lot of 2a plus n minus 1d terms. Now remember, this so far is not exactly the same as Sn. It is two lots of Sn because we've added two copies of the sum of the first n terms. But now at least we've got the same term appearing over and over again. 2a plus n minus 1d, 2a plus n minus 1d, all the way along. We just need to know how many we've got. And of course that is just the same as the number of terms, n. So if there are n items in the list, we multiply by n. Instead of writing out n copies of the same algebraic expression, we just say that algebraic expression multiplied by n, because that's how many we have. And all we need to do now to find Sn itself is divide by 2. n over 2 times 2a plus n minus 1d. This is the general format that is given for this formula, and like I said, it is provided in the formula book for you to use. What is important, just like with anything in the formula book, is that you learn to build confidence knowing when you should use it and how it should be used. We're going to finish with a bit of an example here of modeling with arithmetic sequences and series. So start with Alice's job, has a starting salary of 20,000 a year, but there's a pay increase of 1,500 automatically applied every year. So in her second year, she'll be paid £21,500, and in the third year, 23,000. What kind of questions do you think could be asked about this information? I'd recommend you pause at this point to think about how this situation could be modeled with an arithmetic sequence or a series, and think about the kind of questions you might get. Here's a few suggestions for what happens when you apply a mathematical modeling approach. You identify the requirements, you figure out what you actually need from your mathematical model, you choose a suitable model. In other words, you determine how you're going to set up the situation in mathematical terms. You define your terms clearly. So if you're introducing variables, letters to represent certain values, then make sure it's clear what they are. You construct the model. So you build your equations, for instance, and you apply the model. Maybe you solve or you calculate certain things. Then finally, you interpret your results within the context of the original situation. Here's a bit more information. I'd encourage you to apply the same ideas to this. Ask yourself what kind of questions we could investigate. Now we have Alice with the same starting salary, 20,000, and an annual pay increase of 1,500 every year. But we also have Bob, who gets a lot more in his first year, but he has a smaller pay increase each year. So the obvious question would really be, who has the better deal? And you'll need to think carefully about the kind of mathematical model you construct in order to determine rigorously which one is actually getting the better deal. No matter what questions you choose to ask about the information provided, you're going to find it helpful to set up a similar sort of mathematical model. So you will probably have an arithmetic sequence for Alice's yearly earnings and another one for Bob's. We have first term representing how much they each get paid in their first year, and the common difference represents the yearly increase to their salaries. You'll also need the two formulae, UN and SN. Remember, the SN formula is provided in the formula book for you. Once you've got those, you can start asking and answering questions that might look something like this. When will Alice's salary first exceed £40,000? And then part B, which is worth looking at the beginning as well before diving in. When will her total earnings first exceed £500,000? And it's important here to ask yourself what the difference is between the wording of the questions. The first one's asking about Alice's salary. The next one was asking about her total earnings. And very often you'll find in an A-level exam question like this, there'll be at least one part of it which refers to and relates to the UN formula, and there'll be another part that relates to the SN formula. So every time you see a question like this, see if you can figure out which of those is most likely to be what you need. Well, remember, Alice's salary is the thing that we're measuring with the terms in our arithmetic sequence. So £20,000 is the first term, and that's her salary in the first year. 21,500 will be the second term, her salary in the second year. So question 1A here is asking a question about UN. And we can set it up like this. If we know A and we know D and we know the UN formula, we could substitute the values in and ask the question, when do we get a value of 40,000? Now I've done this as an equation instead of an inequality. It'll come out as a slightly more awkward number, 14 and a bit. But that tells us that the 14th term is not as big as 40,000 and the 15th term is bigger than 40,000. So that allows me to jump to the correct answer of 15 years. When she's picking up her 15th yearly salary, that will have a value which is bigger than 40,000. Now for part B, the total earnings is to do with the sum of the annual salaries. So this one would require the SN formula. And I'm doing a similar thing. I'm putting in 500,000 as SN, and then we rearrange and solve the equation. But you'll notice in this case, the equation is a quadratic. This is because of the way sequences and series can work. If you're adding up terms that are going in a linear progression, then potentially they could go up and then down, like we saw with the common difference of -2. There might be a maximum value for the sum. Now in this case, there will be one answer that makes sense, and we get n equals 16. So we can tell from that her salary total of all the years up to and including the 16th year, that's going to give her more than $500,000 altogether. We could have similar questions for Bob. When does his salary first exceed 40,000? That works out to be 11 years. When does his total earnings first exceed $500,000? And that's 14 years. But This is the really important question, or almost the most important question. When will her salary first exceed his? And then the real kicker, how long would they both have to work for Alice's total earnings to equal Bob's? It's not enough for her just to work long enough to finally be being paid the same this year, but how long until the total amount she's been paid matches the total amount he's been paid? So again, it's a case of thinking about whether we're dealing with SN or UN. And for question 3, we can see it's going to be a UN formula because we're asking about the salaries. So we've got to use the UN formula for Alice. That's this one on the left. You can see the A and the D from Alice's situation. And at the same time, the UN formula for Bob. So Bob is going to be in green, Alice in blue. But when we set those two equal to each other, we find we just have a linear equation. We can simplify and solve, and we find that the number of years is 21. She's going to have to work there 21 years before she's finally paid the same as Bob, because although his salary increase was less each year, he had a significantly larger initial salary. For the next one, how long until their total earnings are the same? Again, because it involves the SN formula, which is a quadratic in n, we end up with a quadratic equation. But we can simplify this, and it turns out to give us something linear in the end. That's because both of them have an n over 2. And the key thing to remember, and this is the same with the previous question, is that n is the same for both. A and D are unique to the individuals, but n is going to be the same. So when we have 2a plus n minus 1d, the n represents the number of years we're waiting. And in Alice's case, this gives us the total amount she's going to make up to and including year n. And in Bob's case, this is the total amount he's going to make up to and including year n. When we simplify that down, we find the final result, 41 years. That's how long she would need to wait. In other words, once she's waited about 20 years until she's earning the same amount, she needs to wait another 20 years before the surplus that she earns makes up for the deficit she had during the original 20 years. And finally, we have a few challenge questions for those of you who'd like to try your hand at these. You can pick any one that takes your fancy and give it a go, see how you get on. And there are also a few questions I would like you to do from exercise 3B, questions 3, 4, 9, and 10.